this video focusing on the 5% rule, which is maybe the most overused thing that students will try to invoke in equilibrium problems. And that doesn't mean you won't see it a lot. It just means that you'll try to use it in places where you shouldn't. And I'm going to try to prevent you from using it in the wrong places. But essentially, when you get to the mathematics of it, you'll see that it simplifies things down so much that your first instinct will be to try it. And what I'm going to try to get into you is no, you're going to check to see if it works before you waste time trying it when it doesn't work. So before we get to what the mathematics actually are, all right, for the 5% rule, what we'll need, and you'll see it when we get to the math, but for now, let's just make sure you understand what the checks are. What you'll need is a small x, all right? If you can look at your setup and you can decide that your x is small, all right, then you know that you should try the 5% rule because it's going to save you time mathematically. So here's what you're going to do to decide that you have a small x. You're going to look, and this is like a rule of thumb, all right? So it kind of works most of the time. So you're going to look for about a 3 order of magnitude difference between the concentrations involved in your ice table and K. So what's an order of magnitude? It's a power of 10. So I just wrote down this quick little example here to kind of show you a situation where you might have a small x. Now you need both of these to be true to have a small x, but let's just focus on the top first. What's a 3 order of magnitude difference? Here I'm looking inside my ice table and I see that I have a 10 to the minus 4th molar. And that's the biggest concentration that I have in that ice table. My K is 10 to the 3rd. So do you see these numbers up here? These will be referenced as an order of magnitude. Like the order of magnitude here would be referenced as a 3 because it's the power of 10. And the order of magnitude here would be the negative 4 because that's the power of 10. The difference between these guys is 7 orders of magnitude, okay? Because to get from 3 to minus 4, you would need to subtract 7. So would that satisfy this first point to maybe try the 5% rule? Yes. If I change this up, and I make this K 10 to the minus 3rd, and my concentrations involved in the ice table, the biggest one is like 10 to the minus 4th, all right? Or don't even say biggest one, like just a concentration involved that involves this small x, and you'll see what I mean when we get to the math part, is 10 to the minus 4. Here, the order of magnitude difference is only 10 to the minus 1. So the 5% rule, it's not going to be sort of by a rule of thumb assured to work. So in that instance, because the order of magnitude difference is not 3 orders of magnitude, we wouldn't try to use it, right? And I'll show you when we get to our mathematical example one more time, just what that order of magnitude difference check looks like, right? If there is that 3 orders of magnitude difference, like that first example we showed, where this was 10 to the 3rd and this was 10 to the minus 3rd, okay, over 3 orders of magnitude difference, right? 3 is the minimum. So if you go over that, you're better than that, so you're good to go. The other thing that you check is that you have to be moving in the unfavored direction. Now we already know how to decide these things. We know to decide which way the equilibrium moves. That's a Q versus K check, right? We know that we can look at K by itself and decide which side is favored, the product side or the reactant side. If you're moving in the unfavored direction and there's at least a 3 order of magnitude difference between the concentrations in K, then your X is going to be small. Let's practice this down here just in terms of a check. So here's a quick little equilibrium that I wrote between A and B. The K is 10 and the Q is 0. Let's look at the K. The K is greater than 1. So we know from our analysis of what K means that the products are favored. So I'm just going to put a little blue star on this side, all right? The products are favored because K is greater than 1. Well, let's do a Q versus K check. So you're given some initial information and you figure out, well, Q is 0, right? So in this instance, with these numbers, Q is less than K. Well, if Q is less than K, in which direction are we moving? We're moving towards the product side, right? Wait a second. We're moving towards the favored side. That means that this move is going to be big. And that means that when we write our ice table, our x's are going to be big. So would we try to use the 5% rule? Would we waste time trying to use the 5% rule in this situation? No, we would not, right? So let's change this up a bit. Let's keep K as 10 but let's write Q as being like 1,000. So K is 10. So no matter what, all right, my star is not going to move because K is 10. That means the product side is favored. Now my Q, so I have a different set of initial conditions. I've changed what stuff is there in terms of A and B to start with. Now I have my Q is greater than K. Which direction are we moving here? We're moving in the unfavored direction. And when we're moving in the unfavored direction, right, we're moving away from our star, we're moving away from what K would like to have, all right? If we're moving in the unfavored direction, then our X can be assumed to be small, as long as there's a 3 order of magnitude difference between concentrations and Ks, all right? So now we'll do an example and show what the 5% rule is, but just kind of realize that you want to do these checks. You want to make sure that this is happening before you waste time doing the 5% rule. All right. Now, what we're going to show you is that the 5% rule saves you time and mathematical sort of manipulations based off of quadratic equations. And essentially, you get to avoid using the quadratic formula. But again, all these checks, they have to be true before you try to enact this mathematical process. So let's take a look at an example to show you what we mean here. All right. So I'm going to write in a reaction down. So let's have CO. Carbon oxygen. Let's have CO, Cl2, which is a gas, in equilibrium with CO, gas, and Cl2, gas. So there's our reaction that we have. We're given that Kc for this reaction is 8.08 times 10 to the minus 4. Right? We're given only one bit of initial information. We're given that we have 0.50 molar of that species to start with. 0 and 0, all right? Go for our CO initial condition and our Cl2 initial condition because we're not given any other bits of information. So let's fill out this ice table and let's see how we'll get a quadratic that we'll have to solve, but then let's invoke the 5% rule and show you how it simplifies the math. So what do? We do a Q versus K. In this instance, hopefully you can see Q is equal to 0. So if Q equals 0, we know which direction we're moving in. We know we're moving to the product side. So in terms of filling out our ice table, we can write a plus X here, a plus X here based off the stoichiometry, and a minus X here. Let's do our check. All pluses on one side, all negatives on the other side, okay? I plus C equals E, 0.50 minus X. I plus C equals E, okay. I plus C equals E, 0 plus X is X, 0 plus X is X. Okay, so now we knew which direction we moved. Here's our K. K is going to be X times X, right, over 0.50 minus X. And you're looking at this and you're saying, okay, well, I know how to solve this based off the last video. This is a quadratic. And you definitely could solve it, and I encourage you to go try to solve it with the quadratic formula because that will always give you the right answer. But let's say I wanted to save time and I knew that this X was small. Now, if this X is small compared to 0.5, then essentially if I have a small number and it's added or subtracted to a bigger number, then you can kind of get rid of that X. So for example, if I have 1,000 and I subtract 1 from it, I'm left with 999. So this is a change, but it's not a drastic change. So if this X is small relative to this number, well, 999 is really close to 1,000. And so what we do is we say, well, let's not even do this math. Let's just keep it as 1,000. So what we're going to say here is, with this example, what if this X is really small compared to 0.5? Well, then this bottom, it can be approximated by 0.5, this denominator here. So that'll avoid having to use the quadratic formula, so that's a nice thing. All right, so how do we decide that this x is small? We do our checks. Let's look at this k. This k is 8.08 times 10 to the minus 4. It's way less than 1. If I put a little star over here, because it's way less than 1, that tells us that the reactant side is favored. All right. Where is our equilibrium moving? It's moving away from the favored side. So does that mean our x is small? Possibly. Now let's look at our order of magnitude difference. This is 0.5, which we could write as like 5 times 10 to the minus 1. What do you see here? You see a 10 to the minus 4. Is there a 3 order of magnitude difference between these species, between the concentrations involved and the K? Can you see that 3 order of magnitude difference? Yeah, it looks like it's there. So we're moving in the unfavored direction. We have a 3 order of magnitude difference between the K and the concentrations. Then what we're going to try to do is the 5% rule. And we're going to stop this problem in terms of solving for our x, but you're going to see, and like I said, I want you to try to do it with the quadratic formula. We're going to see we're going to get the answer real quick. So when we do a 5% rule problem, we like to write down, we're going to assume, because we did our checks, that x is less than, and we even put like 2 less than signs here. We're going to say it's so much like smaller than where we're adding or subtracting it that we're going to be able to neglect it. All right. So that means that we're going to assume that added and subtracted x's are actually equal to 0. Oops, sorry. Added and subtracted x's are equal to 0. We can't do this with multiplicative x's, right? If I have, like doing another example here, if I have 1,000 times 2, right? That's 2,000. That multiplicative value, it changed this drastically. If I have 1,000 minus 2, oh, well, that's 998. That's really close to where we were before. So we never do this with multiplicative x's. We only do it with additive or subtracted x's when we decide that they're small. So we hit our checks. We look here, we're not going to get rid of this x squared because that's multiplying things. That still is an x that would definitely affect the math. But this x right here, man, is pretty small compared to 0.5 based off our checks. So let's rewrite this equation. 8.08 times 10 to the minus 4 is equal to x squared divided by 0.50. We literally just take these and we say they're so small. Once they're added and subtracted, we might as well pretend they're 0. So this, you do not need to use the quadratic formula to solve. This, you're going to take the 0.5 to this side, and then you're going to square root both sides. And what you get is x is equal to 2.009975. All right, and we know it's a molar. All right, we can write it down. Because we know if we have to solve for concentrations, this is what we'll get. For units. So there's 2 significant figures here. Way easier, avoided a lot of math, right? Solve for x in a lot more straightforward way. Why we call this the 5% rule is because at the end of these problems, just to make sure you didn't miss anything, all right, you're going to do this check. All right. And what you're going to do is you're going to find the number where you neglected your x, and then you're going to add or subtract your x to it, divide by that same number. And what you're going to get out is an answer. And what you want this answer, oh yeah, multiply this by 100. The reason we call it the 5% rule is you want to make sure it's within 5% of that number. So this math will give you an answer, and as long as you're within the range, 105% to 95%, you're within 5% of that value, and you're set and you're good to go, okay? Now, this is something Chem 101 will not ask you to do, I don't believe, directly. But again, if you're solving for an x, all right, it's the best way to check to make sure that, yep, all those assumptions you went through in the beginning to decide your x was small, they're valid. Let's apply this to our situation, our example we just got done. You find the x that you neglected. So we took our x and we neglected it from 0.50. So that's the number that would have been affected by that x, but we didn't actually use it because we just decided that x was really small. Now we're going to take this minus 2.009975 times 10 to the minus 2. You know, in the last example, just make sure that I wrote down times 10 to the minus 2. I can't remember if I did. This was our answer. This was our x. All right, so hopefully you caught that error if I didn't write down this times 10 to the minus 2. This is what we're going to do to decide if we're in 5% of this 0.5. Because if we are within 5% of this 0.5, then we're allowed to use this rule. So we do this, and what we're left with is 96%. Are we within that range? Yes, we're within that range. So then this is a check that we do at the end, just a real quick check to make sure that we're within that range and that we didn't go outside that range and it's not more than 5% of this number right here, right? So try to use the 5% rule when it makes sense to. Remember the checks that we did at the beginning. When our x is small, the x's that are added and subtracted, and only those x's, we can neglect, we can pretend they're 0. And then at the end, just try to do this check. Find where you were subtracting or adding that x, all right? And do that math and divide by that number. And if you multiply by 100, you should be within that range. And then you're confident that, yep, this x is small enough to say that this is my actual answer. And again, one last time, you know, a few minutes ago when I was giving you this answer, I can't remember if I wrote down this 10 to the minus 2. Just make sure you understand that this is the answer to that last example that we did, right? 2.009975 times 10 to the minus 2.